Okay. Yes, so here we are with module 1, 2, 3, 4, 5. I emphasize revisiting the course map just simply to understand the broader context in which we find ourselves. So here we are, correlation analysis. And keep in mind that this is a conceptual split in the course. We have descriptive statistics, which describe the sample at hand. So you collect, I don't know, 50 marbles, each of different colors. All right, well, these are ways to describe and characterize and understand those marbles in your jar, or jelly beans, or people, or whatever. It's a way of describing what you have at hand. And overall, descriptive statistics are essentially a collection of tools to reduce the complexity of information produced by data. You have data, and then you have information, and we reduce that. We produce that information through reducing the dimensionality, the complexity of the data. We don't want to look at every passenger on the Titanic. We don't want to look at every single state. We want to reduce our information. And these, as we talked about in the discussion board, some people had asked, well, why don't we use different kinds of measures of spread for a quantitative variable, like the absolute, I don't know, the median or the quartiles and things like that, or 12 other different kinds of averages? Well, part of this is because of tradition. The other part of it is some statistics are more what we call robust than others. Now, robust might mean different things in different contexts, but in statistics, it has this very particular term or connotation or meaning. Robust means that we can have slight deviations from our assumptions, and our model still pretty much works. And that's important to know. So when we talk about what a model is, I think of it as a useful simplification. And some of this is history, some of this is tradition. We use the average instead of, say, the harmonic mean, or the geometric mean, or the Windsorized mean, which are other kinds of measures of averages that are just, tweaking around to find different ways to find the measures of central tendency. But the main point is, regardless of the method, we're providing you with the canonical ones. In other words, if this were a great books class of like the 100 great books of the English language, well, there'd be ones that everyone would probably include, including works by Shakespeare. Well, what we're doing in this class is we're providing you with the canonical tools for statistical analyses. And from here, almost everything else is a deviation from that. And in the sense, pun intended, everything else is sort of a variation on what are the essential tools. So first, I want to emphasize that we're describing the data at hand. And second, that what we're doing in this class, in this first half of this class, is that by describing the data at hand, we're reducing the data to provide us with information. And from that information, we hope to gain knowledge. And one way to conceptualize the production of information is through reduction of dimensionality or complexity. I say all of this simply to emphasize that the concept of correlation analysis and the concept of simple linear regression might appear more complex, might seem somewhat distinct from, say, what we did in the first 2 weeks with categorical and numerical data. But fundamentally, they're the same. They are connected to each other. They grow out of each other. And what I want to emphasize is once you find out a way to describe the data and provide us information on the data at hand, in the second half of the course, right here, 1, 2, 3, 4, 5, in those last 5 modules, we're moving from the data at hand to making claims, probabilistic claims, about data that we do not have at hand. So this is why probability is so crucial. Even in data science, when you might have all the data, you might have millions of data points, but you won't have complete knowledge over time. So a lot of what, say, machine learning does, for example, is you might have all of the records on people on Facebook or Netflix users, but you won't know what they'll do in the future. In political polls, we might know about a population at a particular time points, but we won't know how they will act in the future. Well, that's where you use probability to make informed decisions. And probability is fallible. It's degrees of truth. All right, that's my Sermon on the Mount, so to speak. But I just want to emphasize the fact that these are all related. They're a little different, but essentially just think of that. Think of correlation as just one tool, a common tool. And let's go to I think what I hope to be the major concepts here in the outline I created. So I'm going to stop this share. I'm going to share the screen, and I'm going to emphasize what I said before, which was that we're really going to focus on, do we have this one? No. I want to share the screen, and I want to share just some handouts that I had based on class discussions, because a lot of students had more questions, I think, this week than in previous weeks. Are there any questions you have about what I said in terms of situating correlation analysis within this broader construct, this broader idea of the goal of statistics in part is to reduce complexity. And we do that through numbers, through aggregating numbers, through reducing information. Because that's how I want you to think of a correlation. A correlation is the reduction of information in a systematic way. Okay. So we're going to talk about a few things. If you look at the module this week, I would say there are two parts to it. One is what I call a correlation story. And then the other part is the linear transformation story. We'll talk about linear transformations on the next time. This time we're going to talk about correlations. There's a reason we talk about linear transformations, and it's related to the fact that correlations don't tell us everything. But we'll keep that for later. You can read through the slides, of course. But essentially, I'm going to show this handout, and I consider this to be sort of a highlight reel. So just keep in mind, today we're going to talk about a couple aspects of correlations. First, we're going to talk about scatter plots. What is a scatter plot? Then we're going to talk about covariance. Then we're going to talk about correlations and how to interpret them. After I talk about those three things, what a scatter plot is, what a covariance is, and why covariance is related to correlation, or not why it's related to correlation, sorry. What a scatter plot is, what a covariance is, and how to use correlation, how to interpret it. Only then will I talk to you a little bit about the math, because this is about interpretation. And if we have time, I'm going to talk about this notion that you might have heard that correlation does not imply causation, that correlations are spurious. And there are a lot of spurious correlations, and I've shown that in the discussion board, but it's also a topic that warrants acknowledging. But then I'm going to defend correlation. And that's basically what we're going to do today, and I'll give you some interactive examples. But the main goal today is I want you to leave this section knowing how to interpret correlation, how to judge correlation. And with the idea that correlation, like any tool, can be used and abused. And like any tool, you don't have to be necessarily in the carpenter's union to use a hammer. You just have to be sure that you know what you're doing. So again, correlations are useful, they're tools, but they're not necessarily I think there's my argument is me preaching a little bit perhaps, but my argument is we shouldn't think of all correlations as simply useless or uninformative. In fact, they're quite useful. Okay, so last time we talked about numeric data, and we talked about them in sort of a one numeric data points, right? We talked about histograms and box plots, and we're talking about centrality and spread. Now all we're doing is we're taking that one-dimensional description of one variable of basically spread and of central tendency, and we're going to graph that in a two-dimensional space. And that's the point behind a scatter plot. Once you find scatter plots in the world, you will probably be unable to unfind them. This is from the lecture slides. Scatter plots show relationships between variables, typically two variables. And these are typically two numerical variables because otherwise you'll see just a bunch of jumbled points on one. It won't make any sense, really. You can do side-by-side box plots or side-by-side histograms. And quite often with a histogram, you also see superimposed a linear fit line. And we'll talk about that later. But that's simply because a lot of our assumptions with correlation, especially with correlation, but also with simple linear regression, as the name suggests, those will assume a linear association. And quite often that isn't the case, but sometimes it is. But the point is scatter plots don't necessarily require a linear relationship. Sometimes you'll see a linear fit line on top of a scatter plot simply because it seems to be more informative. So let's take a look at just an example of a scatter plot here with the Old Faithful eruptions and then the warning time between eruptions. Now, are any of you, does anyone know what Old Faithful actually is? I mean, are you aware of Old Faithful? I think I'm trying to present a poll. I think I can do that. I'll figure that out later. The point is, Old Faithful is a geyser in one of the oldest national parks of the United States. It erupts every, gosh, it looks like every 2 or 3 minutes. It's one of my earliest memories as a child was with my father watching this geyser erupt. And you had to wait a few minutes. And it's quite literally just a flat piece of turf ground, and then you'll see this spout of water coming. And it's been occurring for many, many years. You can even analyze it in R. And what this is actually a number of reports of how long is the time between one eruption, which is a spout of hot water coming from the ground or from the earth, and what's the time between that and another. So this is the waiting time between eruptions in minutes. Oh, it is quite a bit, so I'm sorry. And then the eruption duration. So quite often you'd see people aggregate, in this is Yellowstone National Park. It's in Wyoming, the state of Wyoming. So it looks like you'll have an eruption, say, at 60 minutes. Here's about an hour. And then you have one maybe, 35 minutes later, perhaps. So maybe you would wait every 30 minutes or so. And you'll see an eruption. So assuming we'll have an eruption every half hour or so. One interesting question is, well, the longer the wait, is there going to be a larger eruption? That would kind of make sense because there might be some dynamic system operating here. And of course, given its name, it's a regular occurrence. Old Faithful means ever since this geyser was discovered, I don't know how many hundreds of years ago, it's been known to erupt pretty regularly. Not exactly as the histogram as the scatter plot shows, but at a fairly regular yet somewhat stochastic or somewhat imprecise manner. Now, this is interesting because it's pretty information dense. The title simply says Old Faithful Eruptions. But what it gives you is essentially information on the association or relationship between two numeric variables. Keep in mind, last week, if you were just wanted to, we looked at one numeric variable at a time. So if you wanted to do a histogram of the eruption duration, you could do that, and you could estimate the mean and standard deviation of eruption duration. This is the x-axis. In other words, how long is the eruption on average? You could also do a separate analysis with a histogram and with a measure of central tendency and of spread for waiting time between eruptions. You could do that. So that means two different kinds of analyses, each separately. What a histogram does is it takes those two bits of information and puts them together. I said histogram, I meant scatter plot. Scatter plot, the name seems pretty clear. You see a scatter right here. Now, what you see here is an example, a case that I'm going to preemptively state, which is that correlation does not imply causation, but correlation tells us something. And it can be informative. In fact, if you notice, the way I was thinking about this was I was even trying to look at the distance, the waiting time between eruptions by looking at this, by looking at the y-axis, and then by looking at the x-axis. Now, I said before that there seems to be quite often a linear fit trend line. There's also something called like a, what is called a Loess curve, or a, what is it, least something weighted curve. I'm not sure what it's called exactly, what that stands for. But the point is that you could fit this with a linear fit line, or you could fit this with a locally averaged fit line, which simply says, okay, for this little bit of area, it looks pretty straight, and then, oh, it looks like once we get here, it bends a little bit. Right here, right? So once we get here, it bends a little bit. So then what the algorithm does is it simply fits what is about the average at that point in that region. And you know, there are different ways of presenting locally weighted fit lines, but it shows a roughly linear association. It also shows quite a gap here, right? It shows many different aspects of the data, but the main point is there's an association, or rather there is a intellectual connection between the analysis of numeric data for a single variable and then the most common representation of a bivariate relationship in a scatter plot. And you can see scatter plots almost everywhere. I would challenge you to see whether or not scatter plots. And I'm starting with this idea, the rebuttal, that correlation may not imply causation, but correlations will tell us something. And I like this old faithful explanation also because it's a clear example of description. It doesn't tell us necessarily about how other geysers will react or act in other circumstances. It only tells us about the data at hand. And sometimes a unique case is extremely important. I have a colleague who's writing a biography of Lincoln, Abraham Lincoln, the former president. There's only been one Abraham Lincoln. Why wouldn't the uniqueness of that case be important? Similarly, this very famous, well-visited, well-known geyser, it's important for the people who visit it. It's important for understanding it. And there's a good case to be made for those with vested interests in a very particular domain of knowledge or particular school or classroom or group of people that it has particular relevance. In the case of a president, that's extremely important because a president wields enormous power over the country and over the world. So here, description is justifiable. Okay, that's my other sermon, but I'm just simply saying there's an association, or there's an intellectual connection between quantitative analysis of a single variable and then this idea of a scatter plot. And the characteristics of a scatter plot, we can say essentially it's two quantitative variables represented on what we call a Cartesian plane, but really on a two-dimensional space. And three, where each data point in the data set occupies is represented by the coordinates between those two variables. That is to say, this little bit of information, this eruption here, it lasted a little less than 4 minutes, and the waiting time before the previous eruption in that case was about 65 minutes. So this is uniquely, each data point in a scatter plot is uniquely defined in a two-dimensional plane by its x and y axis. This scheme was developed by Descartes, René Descartes, the French philosopher. It's often called the Cartesian plane when it has at the x and y axis the 0 point. And I should emphasize that, it may seem a little elementary, but the x-axis is always the horizontal one. The y-axis is always the vertical one. X-axis, y-axis. They're pretty much exchangeable for correlation, but it's important when you're talking about this for communicating, these kind of things. So we go back to covariance. We talked about covariance before. Covariance, well, what does it do? It gives us the direction of a linear relationship between two variables. Now this should be clear. I just want to be etymologically clear here. How do we know? Well, just co means to be with. So co is with, and variance is how much does a variable vary. When we talk about numerical data analysis, we emphasize both central tendency and spread. And we talk about understanding the ways that a variable in a data set varies. By definition, variation is, not by definition, but it's almost axiomatic that we are interested in variation. That's where we get our information. If there's no variation in a data set, it essentially bounds the data set by some aspect. So if we only looked at, say, states that voted for McCain in this week's mission, then we'd have to look at something else because there's no variation in voting. Maybe you could look at the percentage who voted for Obama, but you couldn't look at whether or not they voted for Obama. You'd have to represent the data in some way so that there's variation. And that's what covariance is. Covariance is an extension of variation. And variation is information, or data really, but we want to reduce that data so that's informative. We don't want just variation without any strictures on it or any kind of control on it. We want to understand what that variation is. We want to reduce that variation to a number that is informative. And that's what variance does for us. Well, covariance is simply, quite fundamentally, how do two variables, potentially more, but in this case, how do two variables vary? How do they co-vary? And what it does is it fundamentally, and burn this in your brain, it tells us the direction of a linear relationship between two variables. Notice I said direction and I said linear. And we'll talk about that with correlation, but direction can be positive or negative. And linearity is an assumption in covariance. If the linearity assumption is violated, then that's a violation of the assumption of covariance. So it's sort of like if the covariance is, if the direction of a linear relationship is positive, that is, as we see in this case, that is as you move from left to right. Oh shoot! As you move from left to right, you might be able to go up or down. this is a positive association. You're always reading from left to right, the scatter plot. This is a positive association. If it is not linear, you're violating the assumption in the covariance statistic. And by violating that assumption, you're using essentially the wrong tool for the wrong job. So for example, I don't know, a handkerchief might be useful if you need to, I don't know, blow your nose or something, or wipe sweat off your brow. But a hammer, it won't help you build a house. You'll need a hammer for that. And part of our job as informed, rational people, as much as we can, we try to use tools appropriately. And that's something you need to keep in mind, that if the linear assumption is violated, then the model is not appropriate. Covariance is whatever units you want to apply that are applied in the data sets. So covariance is, by definition, less reductive than correlation. To put it differently, the magnitude of covariance depends on the units of the two variables. And I say it's less reductive precisely because it does not abstract the units of the variables being used. So you can have a giant covariance and you can have a linear association, but you don't know how relatively strong that is because it's almost too descriptive. A covariance describes the data at hand and how it covaries, but it can only be compared to data with identical units on both the x and the y-axis. So let's scroll back up. Take a look at this Old Faithful eruptions measure here. Remember when we talked about variance? Well, variance uses the units in a single quantitative variable. Well, covariance similarly uses the units of both variables that describe in one numerical coefficient, one measure, the direction of the association. But it does not tell us how strong it is because it depends on the units involved. So the covariance measure by itself requires knowledge outside of the statistic. Here we know the units, but look how they're different. We have eruption duration in minutes. We have waiting time in between eruptions in minutes. If we just had the covariance, we wouldn't know that necessarily. We can't make the assumption that we know aspects about the data unless those data are given. Because we could say, have a covariance measured, say, during 2015, using the same process. We're going to replicate our Old Faithful data over time because we're interested to see whether there's change over time. But if we use different units of measurement for time, say seconds or fractions of an hour, proportions of an hour, 0.5 hours, then we run into problems where covariance cannot be compared beyond the sample. So covariance is strictly within sample description. All we can do is cross samples is characterize the direction of the association, which is whether it's positive or negative. And we'll talk more about that interpretation later, but these are crucial points that are going to be tested time and time again. So from covariance, why are we talking about covariance if it is in fact not that useful beyond the sample at hand? Well, precisely because these are the building blocks. Just as variance leads us to covariance, covariance leads us to measures of standard deviation, and then standard deviation leads us to the famous correlation coefficient. Now keep in mind, I'm going to start with interpretation and only then backtrack to the math, because most of statistics is automated. Computers are smart at doing the very rudimentary clerical work. It's our what the biggest challenge is, in my view, is the semiotics. I'm actually even quoting R.A. Fisher here. He talks about what is called the p-value in 1940 or 1950, and he's disputing an actual correlation, and he says the interpretation is less to do with mathematics, because you have mathematicians interpreting the same statistic different ways, and who knows who's right. And what he does is he makes a very good point, which is that a lot of it has to do with the interpretation and what is your assumption. We often try to forget about that when we do statistics, because otherwise you're stymied by philosophy in a way. But it's important to keep in mind that interpretation is crucial in context. So correlation, if I go back to what I said before, it's a data reduction method. So what does correlation do for us? It gives us the direction and magnitude of a linear relationship. Magnitude is important here. We often talk about effect size. What it really means is it is simply a way for us to compare across events and across cases when those units of analyses are different. That's essentially it. So I can compare, for example, the correlation between heights and weights, and come up with one statistic, which is the measure of association. And then I can come up with a correlation of the association between number of cats and the likelihood of getting toxoplasmosa, which is some sort of, I don't know, environmental toxin from cat ownership. So notice I had to quantify the number of cats here. You can't be categorical, you have to be numeric. And this is how you have to treat the data. Those are apples and oranges. They don't even logically make sense, but I'm using that proof by contradiction as to illustrate that both of those different cases, say numbers of cats and contracting a type of cat-borne allergy, and then height and weight, both of those can be identically represented by the same statistic, and the strength of the associations independently can be compared. And you can say, well, the association between cats and this outcome is weaker than the association between height and weight. So that's what we can do. So when we talk about magnitude, we're actually talking about standardization, comparing across apples and oranges and bananas. But that is also the caveat here. This is where you have to put on your thinking cap, which is, what is the point? Who benefits? So that's important here. And then this whole aspect of a linear relationship is what a former professor of mine would say. He would call this an heroic assumption. It requires some kind of heroic choice to be made. He was speaking ironically. But that's really the advantage of correlation. This is why you're going to always hear about correlation and much less about covariance in the media. So let's talk about what correlations do. They can basically be positive, they can be negative, or there can be no correlation. Look what we're doing here. As I said before, the scatter plot describes two quantitative variables on an x and a y axis. That's what we see here. Horizontal, x, vertical, y. Horizontal, vertical. And correlations are meant to be read, scatter plots are meant to be read left to right. So positive correlation means if you're moving from left to right, you're going up. Positive means you're going up the slope. Negative, left to right, you're going down the slope. No correlation. In the advent of no correlation, it looks like a cloud of data points, cloud of mosquitoes. It's flat. Nothing is flat. Negative is downward slope. Positive is going up. And you're reading it from left to right, interpreting two quantitative variables, x and y axis. So here we have different directions and magnitudes, but here we're really talking about different directions. technically the covariance can tell you positive, negative, and essentially no correlation, because if you have a covariance of 0, that means nothing. So we're really just talking about different directions, and we're talking about whether or not there's nothing or something. Now, if there's any something, which there almost always is any something, covariance is not going to tell you about magnitude. So this is how we go down a little bit. It's a little bit harder to see, but let's see if I can zoom in. I want to show this and emphasize that you can talk about different kinds of strength. And the strength is actually how linear they are, how much they deviate from a line that you could draw on the Cartesian plane. This is a perfect positive correlation. What that means is for every x point, you know exactly what the y point is going to be. 100% prediction. That's a correlation of 1, it's positive 1. A strong positive correlation is where, okay, if you know, knowing what x is, you're going to be pretty close to what your y is, right? So you'd bet probably an 80% probability or 0.8 probability of y. Notice I'm talking about probability already. This is why probability is so central. A weak positive association or correlation tells us, okay, for this data point or for this value of y, what does it tell us about our outcome? It's not as precise. There's a lot of variation around here. Same with the negatives. So you can sort of see the perfect positive and the perfect negative. When we say perfect, we don't mean this morally, we just mean this in terms of precision. And perfect positive simply says there is a one-to-one correspondence between our linear assumption and an outcome with that statistic. Weaker ones, there's more noise. If you've ever read Nate Silver's book, this signal and the noise, perfect positive and perfect negative correlations have all signal and no noise. The noisiest is when there's no correlation, and weak correlations have more noise. So the noise goes from outward to inward, and then you go from positive to nothing to negative. So this is what correlation does that covariance cannot. And let's go, but this of course assumes linearity. This is why we started off with scatterplots, because if you just start off with correlation coefficients and stop there, which I've seen quite often, you will be very, very disappointingly misled. So let's take a look at the linearity assumption. In class, we talked about what is famously known as the Anscombe's quartet. The point here is that all 4 of these data points, so all 4 of these scatter plots represent the same correlation coefficient. Well, that's terrible news. Right? This looks like this is definitely nonlinear. This is somewhat linear but noisy. This is linear but with an outlier. If we remove that data point, it might be accurate. This is so off the mark. Your map is of Atlantis, right? And I always often refer to maps and cartography because I always think of models as maps or ways of representing something. It's not the territory itself, it's a representation. It's a way of reducing the data, but it can be misleading if we don't look at it graphically, if we don't compare different kinds of statistics. So just keep that in mind. We do have that linearity transformation. This takes us to the other part of this week. How do you deal with, say, a nonlinear yet somewhat, continuous association? Well, there are ways to transform through linear transformations, through, say, doing adding, basically transforming each variable or transforming a variable in particular so it more approximates a linear association. We often do that in statistics. So you can linearly transform, say, these data. These data, you probably want to present it both ways, right? You would want to present it with and without the outlier and describe whether or not your findings substantively changed. And someone has a question. Sorry. Yeah, someone asked, if we, on the third graph right here, if you look at this one with the outlier, on the third graph, if we remove the outlier, would the correlation be affected? Yeah, of course it would be. So now, but the question we want to ask ourselves is, because we really can't do a linear transformation over the entire distribution of the data, and that's because we have one that is not like the others, there's nothing we can do with the entire data set or with the entire association with a linear transformation or a logarithmic transformation or some kind of function. We can't just apply something to linearize it. What we'd have to do then is we have to, I think the most effective route would be not simply just to drop it and then not report what happens, but instead compare what happens to the correlation and how much it changes if and when we drop it. Now, what do you think it's doing here? Well, this correlation, if we were to remove it, what is this correlation doing? It's increasing. It's exaggerating the strength of our association because it's pulling the rest of these people up. If you recall, I spoke about averages as being misleading precisely because of outliers. Well, this is a good case of an outlier that pulls a bivariate relationship in a way that misrepresents the overall distribution. So this is a misrepresentation of the overall distribution due to an outlier. This is an adequate yet imprecise estimate, which is okay. This is what I'd expect. The second figure in the quartet mischaracterizes the shape of the distribution as nonlinear. And this one here essentially mischaracterizes both the shape of the distribution and produces an outlier. So even if we remove the outlier, it's not adequately represented by a correlation coefficient. And this is actually, I think, quartet number 4 was, if I collected these data or saw these, I'd be the most worried if someone had published a paper looking at correlations and I did a scatter plot and I saw this. I would think, oh my gosh, this is bad news. Notice, by the way, when I talked about variables, we want them to vary. When I say we want them to, I would say it's just not informative. This is why we often norm tests. If you take a standardized test, they have what they call ceiling effects. If everybody does well on a test, technically, a lot of statisticians or test makers aren't interested in or find that to be a problem, because if everyone does well, then we can't separate and distinguish people. That being said, I think it all depends on the context. What's the point of the test? Okay, any other questions about the linearity assumption? I think the main point is it can be represented in many different ways. It's not a fatal flaw, but it requires us to look at the graphics and to treat it differently. Don't just look at the numbers, just look at the data. So I talked about how to interpret it visually. Now I'm giving you slide 50, I think 77 in the lecture today. Just remember that a standardized measure correlation ranges between -1 and 1 and is unitless, while covariance can be any number and is expressed in the units of the two variables. Here we see a magnitude of correlation. Keep in mind that when we talk about magnitude, a very weak correlation goes from 0 to 1, and a very weak positive correlation is from 0 to 1. A very weak to extremely strong correlation that is negative goes from 0 to -1. But when we talk about magnitude, it's an absolute value. Whether or not the association is negative or positive, the strength is symmetric. So a strong correlation of 0.5, well, I'll give you an example. A strong correlation, extremely strong correlation of 1, which is the upper bound of the correlation, and -1 simply show the same association, just with the x and y axes reversed. So direction is useful, but it can also be exchangeable. It can also depend on the units there. These are not hard and fast rules, but there may be some questions that require you to consult this, because I think it's It is a matter of interpretation, and it is a matter of context. But this is pretty much in the clear, that a very strong correlation in the social sciences is 0.6 and above. I'm almost always worried about extremely strong correlations, because then I think there's something funky with the data. Why standardize? We'll skip the math, except just to say that why is it standardized? Why is it unitless in a way? Because it's expressed in terms of a ratio. That's, I think, this simplest way. We can revisit this next time, but think of it just in terms of you take covariance, how two variables vary, and then you divide it by their units. Voila, you get rid of any kind of particularities. You standardize the variation, and this is the correlation coefficient R. It varies from -1 to +1. I was going to play guess the correlation. I have that posted to the site, but take a look at it yourself, and we'll start off that tomorrow. And then tomorrow we'll also talk more about why correlation is not causation. And we'll talk about this idea of spurious correlations. And then we'll continue with linear transformations. And I'm going to end on this. Linear transformations are crucial precisely because we don't have to throw out data and analysis just like this, just as we might consider in this second quartet, in the second quadrant right here that I'm circling. We can provide a linear transformation to approximate the model. We're not misrepresenting the data because we're going to tell people that we're standardizing it in a way, but we're just making sure that the model assumptions are not violated so we can better understand the data at hand. Because if the assumptions are violated, we're misled. If we can build statistics that are robust, or if we can transform the data in ways that don't violate the assumptions, then we have more information. Then we're adequately and principally, in a principled manner, reducing the data and transforming data to information. I hope you found that to be useful, and I'll share the slides after the next section, because I'll add to it. Thank you very much. Now, if there are a couple of questions, I will ask those as well. Someone asked, on a graph that has no linear association and there is an outlier, but we remove the outlier, what happens to the, we answered that, yes. Typically, it depends on the outlier. I just wanted to elaborate on that. Here we have, if we remove the outlier, it'll decrease the correlation, but if this were below the rest of the gang, you'd actually see an increase in the correlation. That's why you always have to look at the data. Okay, any other questions? I know someone had a question on the mission. I think this will help you at least understand and interpret the stats behind it. Okay. Thank you very much, and I'll see you next time. I appreciate all of you attending. Thank you very much.